Dear students, welcome to today's online class. In the previous two classes, we had made a brief outline of what spectroscopy is. From today onwards, we will discuss the details of three different types of spectroscopy with special emphasis to their application. Today we start the first one, that is IR, infrared or vibrational spectroscopy. We have to discuss various fundamental principles related to this spectroscopy. What is the origin of IR spectroscopy? Consider a molecule, for example, HCl. You know that this is a polar molecule. Chlorine being more electronegative will withdraw electron towards it, get delta negative charge, and this get delta positive charge. So it has a dipole moment. Okay. Now, this HCl molecule is not having a constant bond length. It is that the bond length keeps on changing. From this equilibrium bond length, it keeps on increasing. That is called stretching, extension. Come back to the mean position, then contract. This keeps on going. This is called vibration. Vibration of a molecule. It is something like a spring. Two bodies are connected by a spring. Right? You might have learned about Hooke's law in connection with this stretching. So this vibration of HCl molecule will result in change in the bond polarity or change in the dipole moment. There will be fluctuation of polarity or dipole moment, okay, due to this vibration. So this vibration of this molecule give rise to different vibrational energy levels for the molecule. So what is IR spectroscopy? What happens if you are giving IR radiation? The molecule which is originally in the ground vibrational level naturally will absorb IR radiation of suitable frequency and get excited to higher vibrational level. This is what is happening during vibrational spectroscopy. So we can say that vibration spectroscopy involves transition of molecules from lower vibration level to higher vibration level by absorption of IR radiation, and these transitions are governed by what is called quantum mechanical selection rule. We have learned about what is selection rule in the previous class. Remember, all spectroscopic techniques or techniques are all basically quantum mechanical problems. So there will be some quantum numbers associated with every spectroscopic techniques. So I repeat, IR spectroscopy involved the origin, the basic principle behind IR spectroscopy is that it involves transition of molecules from lower vibration level to higher vibration level, absorbing IR radiation of suitable frequency, which is governed by quantum mechanical selection rule. Now, coming to the IR region used for this study, see, in VIBGYOR, the visible region, that is VIBGYOR, next to red comes IR, okay? That is called infrared, the region next to red. This is actually of three parts. We can divide IR into three parts. One is called near IR, means near to the red region, and then it is middle IR, and this is far IR. Okay, this far IR ranges from 50 to 667 or roughly 700 centimeter inverse. Remember, in IR spectroscopy, conveniently we use centimeter inverse or wave number as the unit. Middle IR ranges from 667 to 4000 centimeter inverse, and this near IR is from 4000 to 12,500 centimeter inverse. Remember, for IR spectroscopy, this is the region made use of. So IR spectroscopist is interested in this region, middle IR, that ranges from 667 to 4000 centimeter inverse. That is used for this study, this technique. Okay, next about what are the different types of vibration. I told you the origin of IR spectroscopy is what? Vibration of molecules. What are the different types of vibrations? There are two different types of vibrations shown by molecules. Vibrations are of two types. Basically, one is called stretching vibration, stretching. The other is called bending vibration. Okay, what is that? For example, let us take a molecule that is water, H2O. A simple example, H2O is bent in shape and it has a particular bond angle, 104.5 degree, you know that. Now, stretching vibration means here what happens, these two bonds get elongated. As I said earlier, the two bonds in water molecule, this OH bond get elongated, this also get elongated, come back to mean position and then contract. So this kind of vibration, this is the vibration taking place in water, what is called stretching vibration. The point is that during stretching, what is changing? Change in bond length takes place. Change in bond length. Okay, is it clear? So bond length is changing during stretching vibration. As I said earlier, HCl also, HCl, the bond length, there is an equilibrium bond length from which it keeps on increasing, come back to mean position, decreases, come back to mean position. There is one cycle of vibration. So this kind of movement, that is stretching vibration. So stretching vibration is the one in which there is change in bond length. And what is bending? Here, as I said, this is having bond angle 104.5 degree. So what can happen is that here these two bonds can undergo another type of vibration, that is, it moves like this, it goes out and comes back like this. It's very easy, simple to understand. See, this is a bond angle. What happens? Bond angle increases from this position and come back to the original mean position and contract, go back like this. This kind of movement is called bending vibrations. So in bending vibration, there is change in bond angle. Change in bond angle, that is bending vibration. Okay, so there are two types of vibrations. Now, during these vibrations, the condition for a molecule to be IR active, what is the condition? Which types of molecules are showing IR spectroscopy? Do all molecules show IR spectroscopy? No. The necessary and sufficient condition for a molecule to show IR spectroscopy, or for a molecule to be IR active, or for a molecule to absorb IR radiation is that there should be change in dipole moment. Change in dipole moment. Change in dipole moment during the vibration. During vibration. So during vibration, whether it is stretching or bending, there should be change in dipole moment for the molecule, so that, as I said earlier, in the case of HCl, it is already having a dipole moment, and when it undergoes stretching vibration, what happens? There will be fluctuating dipole, correct? The dipole moment keep on changing. So when there is change in dipole moment, there will be an electrical pulse created in the molecule. I have told you at the beginning, at the very beginning, that spectroscopy involves interaction between the radiation and the molecule, right? What kind of interaction? It can be electrical or magnetic. In IR spectroscopy, is an electrical interaction. You know that for the electromagnetic radiation, there is an electric component. Electric wave is there, And also there's a magnetic wave, also mutually perpendicular. So the electrical component of this radiation can interact with the electrical pulse generated in the molecule during vibration, so that absorption takes place and the molecule give IR spectrum. So example for such molecule is HCl, of course. It is polar and vibration will result in change in polarity. H2O, NH3, these are all IR active. Whereas what about molecule H2? It is non-polar, right? There is no polarity because both atoms are same. Even if it is vibrating, there will be no change in dipole moment. Remember, dipole moment is given by the equation mu equal Q into R. Charge into distance between the charge. There is no charge at all. Like that, N2, F2, all homonuclear diatomic molecules will be IR inactive. Okay. The next is about another important aspect of any spectroscopy is the selection rule. Right? That means which transitions are allowed according to quantum mechanics. For that, we consider the energy diagrams. See, there are two types of vibrations possible for a molecule. One is called simple harmonic oscillation. Simple harmonic oscillation. That is, if an oscillation, if a vibration is obeying Hooke's law, if it is obeying Hooke's law, it is said to be simple harmonic. In that case, the energy diagram, that is energy is plotted against internuclear distance. See, in the case of a vibration, one variable is the distance, it is changing, and energy of the system is also changing. The energy diagram, the vibration energy is having this kind of shape. It's a well energy it is there, and if we show various energy levels, we can see that if the vibration is simple harmonic, we see that the energy gap is same everywhere. These equidistant energy levels are obtained, and as I told you in quantum mechanics, when we solve this problem, we get an quantum number that's called vibrational quantum number, we have mentioned earlier, and that is represented by the letter nu, and this, it can have values from 0 to 1, 2, 3, etc. This is the ground vibration level, nu equals 0. Then first excited vibration level, second level, third level, like that. This is the kind of energy diagram for a simple harmonic oscillation. In this case, what about the transition? Normally, molecules will be mostly in the ground state, correct? To be more stable, molecules will be in the ground vibration level. There's an interesting point to be noted here. See that the ground vibration energy of a molecule is not 0. See, energy is not 0. It is having a specific definite value. This is called 0 point energy. What does it mean? I've told you earlier in the previous class again. The vibration of a molecule cannot be stopped altogether. It will have a little bit of vibration even at the lowest temperature. So there will be a minimum vibration energy that's called 0 point energy. So from this, molecule can get excited into this level only. That is the selection rule. So next is about selection rule. What is the selection rule in the case of IR spectroscopy? Selection rule. What does selection rule say? What is a change in quantum number which is allowed during transition? That is what is selection rule, which restrict the number of transitions. It is that for simple harmonic kind of oscillation, selection rule delta nu is equal to, it's so simple, plus or minus 1. What does it mean? Here, plus indicate absorption, minus indicate emission. Generally, in molecular spectroscopy, we are concerned with absorption kind of spectroscopy. So the point is that an allowed transition is that from nu equals 0 to nu equal 1, molecule can go from 0 to 1 only, not to 2. It is restricted. If suppose the molecule is in 1, it can go to 2. If it is in 2, it can go to 3 only. This is the selection rule. So vibrations which follow this rule is called allowed transitions, which will be very intense. See that all these energy gaps are same, correct? All these are having same separation. So the vibrational spectral line in this case will be only one. Whichever is the transition, mostly this will be the transition because most of the molecule will be in the ground state. Even if it is in some excited state, then also the energy required for the transition is same. So you will be getting only one single line in this kind of simple harmonic oscillations. But by and large, molecules are found to undergo oscillations violating Hooke's law. That is the actual practice. Most of the molecules, when they undergo vibration, it doesn't completely obey Hooke's law. That means, suppose this HCl molecule, it is undergoing stretching. According to Hooke's law, the restoring force is directly proportional to the displacement. That comes from physics, of course. So when bond length increases, and it comes back and decreases and it keeps on going, Hooke's law is not perfectly obeyed, in which case that's called unharmonic oscillation. That kind of oscillation is called unharmonic oscillations. Okay? Okay. In this case, the energy diagram is found to be a little bit different. It comes like this. See? It comes like this. Something like this. See, this is the internuclear distance. Suppose we have HCl. Okay? It undergo vibration. When the distance decreases, that is undergo compression, okay, fine, energy is increasing. This part of the energy curve is not much different. But on this side, that means when it elongates, what happens? Energy increases, but then it comes to a constant value. Can you say what is it? When a bond is stretched, elongated, what could happen? It can dissociate. The bond can break and then energy comes to a constant value. This is a kind of energy diagram obtained for a molecule which undergo oscillation violating Hooke's law, or it is underway unharmonic oscillations. In this case, the energy levels are a little bit different. This is the first level, suppose. The second one, third one, like that it goes. See, what is happening here? What is happening here? The ground vibration level nu equals 0. Then 1, 2, 3, 4, etc. What is it? What is happening? Energy levels comes closer and closer and they merge all at this point. Okay? So, in this case, so the energy gap is not same. In this case, if a molecule is in nuclear 0 state, it can go to 1. Okay, that is the selection rule in this case, delta nu is equal to plus or minus 1. That is there. But in addition, in the case of unharmonic oscillations, the selection rule is not only this. There is also delta nu equal plus or minus 2. Transition is also possible. Plus or minus 3, etc. That is the difference. In the case of unharmonic oscillation, selection rule is a little more relaxed. More transitions are possible. It is because, why we are thinking in that way? Because when you take the IR spectrum of a molecule, we find so many peaks. It is not just one peak we are getting, so many peaks. So from that observation, we come to the conclusion that vibrations are quite unharmonic and there is more transitions possible. See, when the energy gap is decreasing, there is more chance for transition, right? So here, this transition now is called fundamental transition. Fundamental transition. What is fundamental transition? Obeying this selection rule, delta nu equal plus or minus 1. The vibrational quantum number can change by 1 unit. From nu equals 0, it can go to 1. From 1, it can go to 2. That is fundamental transition. And that is most intense, of course, which is most likely transition. But in addition, in anharmonic oscillations, there is also additional transitions possible corresponding to delta nu plus or minus 2. What does it mean? From nu equals 0, it can go to 2, that is plus or minus 2, or plus 2 it means here. And what is plus 3? From 0 to 0 it can go to plus 3 also, and etc. But it then probability decreases, so mainly we get these transitions. These are called transitions having delta nu plus or minus 2 plus or minus 3 means higher transitions. They are called overtone transition. So there are two types of transitions, fundamental and overtone transition. So corresponding peaks obtained is called fundamental band, fundamental peak, and others called overtone peaks. And here this is the fundamental, right? This is fundamental. This is called first overtone. In overtone we again classify first overtone. This is called second overtone, etc. If we take the IR spectrum, you will be getting more peaks. Suppose this is corresponding to this fundamental transition. Suppose it is nu 1. Then roughly this is double. You get first overtone, then you get second overtone, like that. Roughly it will be 2 nu 1, there will be 3 nu 1, roughly, not exactly. So like this you get more peaks. So that is the case of anharmonic oscillations. So two types of vibrations are there, fundamental and overtone transitions. That's a selection rule in the case of IR spectroscopy. More about IR spectroscopy in the coming class. Thank you.